All right, well, welcome. Thanks for all of you for joining us today. This webinar is about a dust collection system design for laser cutting, which is one of many educational webinars for engineers that we deliver here at Donaldson. My name is Amy Miller. I'm a training manager here at Donaldson. We're going to start off today's webinar by briefly discussing a few fundamental concepts for a dust collection system design, specific, of course, for laser cutting applications. And then we're going to review the primary components for a system design, which includes hoods, ducts, collectors, fans, and electrical controls. And then we're going to finish up with a Q&A session, everybody's favorite part. Just a heads up that it takes years of experience and education to become proficient in system design. The goal of this session is to give you an overview of the basics. In case you aren't familiar with Donaldson, we've been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who actually invented the world's first tractor engine filter. Today, we're one of the largest providers of unique technologies, and we excel in providing high-quality filters and equipment. We pride ourselves in having a global reach with a local touch. Our world headquarters is in Bloomington, Minnesota. We have 56 manufacturing plants and 22 distribution centers around the world. If you think of questions throughout the webinar, please type them into the chat box, and John and Mike are going to answer them towards the end of our session. And then during the webinar, they're going to ask you a few questions, and you can respond with a reaction emoji. You can access those by clicking on the face icon at the bottom of your screen. And with that, I'm pleased to introduce our featured speakers today. Mike Rentz is a key account manager here at Donaldson. He focuses exclusively on the OEM market. He works closely with large manufacturers, such as those who make laser cutting equipment, to help them provide turnkey solutions for their customers. Mike, did you want to say
hello? Happy to be here, Amy. Thanks. Yeah, happy
Excellent.
to be here, Amy. Thanks for everyone joining today.
Perfect. We can hear you great. Thank you. And then John Danio is a strategic account manager. He leads our strategic team that works closely with large multinational customers as well as our OEM team. And he works closely with engineering firms. And if you've attended a webinar in the past, you'll probably recognize him.
Yeah, good morning or good afternoon, depending upon your location. Like Amy said, I help lead our monthly webinars and looking forward to today's session on laser cutting. All right, I'm going to kick us off here. And before we get started, we'd like to ask everybody what their level of experience is in designing dust collection systems for laser cutting operations. It kind of helps us understand your level of experience. So if you can click the reaction emoji that best aligns with your level of experience. All right. Yeah, looks like we have a variety of experience, and I will use that as we move forward, and hopefully we cover all of your needs. And again, as questions come up, please put them in the chat box, and we'll be happy to answer them at the end of the session. So let's review a few basic concepts about system design. Here's a typical diagram of a dust collection system. A fan or a blower creates an airflow, which is used to capture dirty air from the laser table. Then the dust is conveyed through a series of ducts to a dust collector. Here, the contaminant is filtered out, and the clean air passes through the filter media to the fan, where it's discharged into atmosphere or back into the facility. And we must always make sure we're incorporating the electrical controls, and they're the brains of the system that help control the powering on, the automated cleaning, or sending an alert to the operator if there's an issue. If one component of a dust collection system is poorly designed, the whole system is affected. Here's a real-world example of a dust collection for a laser table. Okay, technically it's a plasma table, but they're both metal cutting tables, and a great example of what you can see the entire system here. As you can see, it has a downflow airflow draw. And you can also see the ductwork on the right side pulling air through a custom spark mitigation system into the dust collector. After the spark mitigation system, the airflow will move through the ductwork into the dust collector, and again in a downward path. You can also see a fan at the top with a silencer coming off the side for noise reduction, as well as electrical controls that may or may not include a VFD for automatic airflow control, and Mike will talk a little bit about that later on. So there are two main types of systems used for laser cutting applications. One is a cellular system where one dust collector is connected to multiple machines, or a single machine system where each machine has its own dust collector. A single machine is much more common for laser cutting due to the high cost of the laser tables, and most companies only have one in their facility. So if there are more than one, a cellular system is often recommended. So when specialists like Mike design a system, there's lots of factors and variables to consider. It's actually much more complicated than one would think. The publication shown here is the Industrial Ventilation Guide, which is an indispensable resource for proper system design. The vent manual is written by the American Conference of Governmental Industrial Hygienists, or the ACGIH, which is a nonprofit scientific organization that advances occupational and environmental health. They offer multiple courses throughout the year on system design, using the Vent Guide as a textbook. Most of our folks have attended this course over the years, and we actually have a few Donaldson staff that are instructors. The ACGIH guidelines are considered by most in the industry, including OSHA, as a standard for proper ventilation design. Things that we need to consider when designing a system include material that's being collected and the properties of the dust being collected, the application being utilized, the process conditions. Is it humid? Do the workers use personal fans? Does the facility have conditioned air? What are the hours of operation? Will the system be used continuously or intermittently? What's the total airflow requirement? What location or environmental restrictions exist? Do they have compressed air available? Does the collector need to be located indoors or outdoors? What's the footprint and height requirements to make sure it can fit? Has the dust been tested for combustion or flammability? If it is, what's the NFPA standards that apply? And does the plant have expansion needs that we should consider when we first design the system? So as you can see, there's a lot that goes into designing a system. There's many different technologies and formulas that we use in dust collection system design. The most basic and widely applied being airflow. The formula is Q equals V times A. The Q is the volume of air flowing through the system, often referred to as the CFM, the cubic feet per minute. To get the airflow, we multiply the velocity of air, which is the measure of linear speed of an object, by the area of the hood or duct that the air is flowing through. This formula is one of the basic building blocks of dust collection system design. There are different types of air velocities that are important to maintain in a dust collection system, including capture velocity, which is the speed of the air at the hood or the area of generation. In this case, it's the laser table. The duct velocity, which is the speed of the air flowing through the duct. The filtration velocity, which is the speed of the airstream as it enters and passes through the filter media, also referred to as the air to media ratio, or AMR. The interstitial velocity, which is the speed of air in between the filters. All these need to be managed to appropriate levels for proper filtration. Mike will cover this a little bit later in the presentation as well. And just a few more terms here. As I already mentioned, AMR is calculated by taking the actual CFM divided by the total filter area. It's expressed as a ratio, such as 6:1. So 6 cubic feet of airflow for every 1 foot of filter media. And static pressure, which is the resistance to airflow in a system from things like the collector itself, the filters in the collector, which can create more resistance when they're dirty, the hoods, and the ducts. So let's do a little overview here of laser cutting if anybody isn't familiar. A laser cutting machine is a device that uses a focused laser beam to cut through materials. It's a versatile tool used across various industries like industrial manufacturing for precise and efficient cutting, engraving, etching of a wide variety of materials such as carbon steel. As you can see, the laser beam is generated and focused on the material to be cut. The heat from the laser creates a precise cut and is controlled by a CNC system. Laser cutting machines are either open or closed. On the left, you can see a machine that's open. And on the right, you can see one that's enclosed, so it has a custom hooded closure over the top of it. It's an important difference when you design a system, because these machines will be sized differently. And Mike, again, will cover this a little bit later. The two most common laser cutting systems are CO2 and fiber. Fiber lasers offer advantages over CO2 lasers, particularly when cutting metals due to their higher efficiency and speed, especially with thin materials. CO2 or oxy-fuel lasers, on the other hand, are more versatile in cutting non-metallic materials and can handle thicker materials. It's also an important distinction when sizing a collector. The fumes being generated from a laser cutting system are submicronic in size. The particulates are as small as 0.01 micron and present a fume that is in low bulk density, so it means it's very light. The fine and light particulate can easily agglomerate or stick together, and when compacted, form an impermeable layer on the filter media surface. It also may be toxic when breathed in and can cause a host of issues, including certain types of cancer, eye, nose, mouth, skin irritation. The metal fume from the laser cutting process can be both combustible and explosive. So we'll talk about that here in a second. As most of you are probably familiar with the fire triangle on the bottom left, if the dust or fume is combustible and it mixes with air, like the airflow coming off the dust collector, and an ignition source, it can result in a fire. If you add in dispersion of the dust, which occurs frequently in pulse cleaning of the collectors, you can get a flash fire. And when you add in confinement of the dust, so the dust collector housing itself, you can get an explosion. I wish I could spend more time on this. It's a really complex issue. We actually have a whole nother webinar on combustible dust that you can watch on our website. For now, it's important to know that laser cutting fume may be combustible and explosive, and it's an important design consideration. We typically need to know things like who the process owner is, who the AHJ is, and then information such as KST values from the DHA to help customers make informed decisions on the best mitigation systems. So as mentioned, there's a lot of important reasons to control dust and fume generated during laser cutting operations. Obviously, the safety concerns and hazards I just mentioned, improving the overall air quality for employees, exposure control, so really reducing the potential dust in the breathing zones where the workers operate, environmental concerns such as EPA standards for outdoor exhausted environmental air quality and outlet emission requirements, cleanliness concerns, the overall cleanliness of the facility, and quality of manufacturing, because that dust can interfere with the laser cutting performance. So let's get more into the designing the specific components, and Mike, we'll let you start off with hood design.
Thanks, John. Yeah, so we're going to kick things off with hood design. It's actually the first system component you will size when designing a new system. Also, on a side note too, just a quick reminder, please do submit your questions into the chat box as you think of them, and then we'll address them more towards the end of the presentation, and we appreciate your participation in that. All right, so when we're talking about laser table applications and sizing, you saw the picture earlier where there was an open table and then an enclosed table. So when we're looking at the tables, the hood itself is incorporated into the table. So essentially air is pulled down through the table as a downdraft and into the duct system inside the laser. And then from there, it makes its way into the dust collection system. The airflow or CFM being pulled through the system is determined by the manufacturer. It's based on a few different things, including size of the table. Larger tables generally are going to require larger airflows. If it's open or enclosed, open would require more airflow than enclosed in most cases, and the power of the laser itself. Laser powers, as many of you may know, have been advancing rapidly over the last 5 years and currently typically range from 3 kilowatt to 30 kilowatts of power. So when sizing a dust collection system, a 3 kilowatt system will require less media area on the filters than, say, a 30 kilowatt system. And if you'd like, give us a thumbs up if you've designed a system that's over 15 kilowatts, and a thumb down if you have not.
Looks like most people have not gone up to that size, Mike. So this will be new, but I'm sure it will be coming in the years ahead. Oh, a couple have. So there we go.
Perfect. Good. A good mix. All right. So no matter the power of the laser, when determining the required airflow at the table, one of the main design factors is called capture velocity. So this velocity is what's required at the point where contaminant is generated in order to gain control of the contaminant and direct it through the ductwork and into the dust collector. There are standards recommended in the vent manual for laser cutting, and generally this number is going to be between 150 and 200 feet per minute.
All right, sorry to interrupt you, Mike. Just a quick reminder, again, to make sure you submit your questions into the chat box as you think of them, and we'll address them towards the end of the session. You probably needed a quick drink of water there, Mike.
Yeah, perfect. I appreciate the break. Yeah, thanks, Amy. All right, so once we move the contaminant from the laser table itself, the goal is to move it into the filtration system through a series of ducts. So when we're looking at duct design, a properly designed duct system should include a few different things. So it should be able to pull the minimum airflow required at the table. It should be able to maintain velocities required to transport that material through the duct without dropout to the collector, and use the least amount of energy possible while minimizing any wear and tear on the duct components. The minimum duct velocity is a critical design factor. It is the lowest velocity where all contaminant will be transported through the duct system. For laser cutting, we typically are looking at using between 3,000 and 4,000 feet per minute conveying velocity in the duct. So two different scenarios. If the duct velocity is too low, as you can see in the image, the dust could settle out within the duct and cause problems such as safety issues, and can ultimately lead to total system failure, meaning if you're looking at that picture of the ductwork, imagine that dust being collected in the ductwork and then getting too heavy and the ductwork actually collapsing and falls. If the duct velocity is too high, it won't necessarily create any safety concerns, but it will require more energy to move the air through the duct. So ultimately, having too high of an airflow could impact the size of the system fan, as well as create issues such as increased noise, abrasion, or wear and tear. Just a few quick pieces of advice when it comes to duct type. So rectangular duct, which is commonly used in HVAC applications where you're moving only air, is not necessarily a good option in industrial applications because it could allow dust to settle out in the corners of the duct. It is okay to consider, though, for the clean air side. When specifying industrial duct systems, make sure to call out round, heavy-duty industrial ductwork. Most dust collector applications will use a class 2, 3, or 4 ductwork, which are designed to SM-ACNA standards. Another type of ductwork is spiral duct. So spiral duct tends to leak air and could impact your design airflow by roughly 10%. And if it's used outside, could also provide a prime source for water to enter the ductwork and get into the dust collection system, which in cartridge collection is something we really want to avoid. I've seen it used effectively if it's heavy enough gauge and smooth on the inside, but definitely something to use with caution. And be aware that flexible duct requires significantly more energy than traditional hard ducting, so we recommend really minimizing the use of flex duct as much as possible. And then lastly, you'll want to avoid T's and 90-degree angles as much as possible. So when you're looking at this slide, picture on the left are different elbows. So we would prefer elbows that are 2 to 2.5 diameter, centerline radius, except where space may not permit, in which case you can use a 1.5 diameter centerline radius, and that is also acceptable. But if the elbows are mitered 90-degree turns, as you can see on the bottom image, that's something that you're really going to want to avoid because all the air has to slow down, turn, and then speed back up again. This is going to create a ton of turbulence in the ductwork, which adds more energy consumption and a higher static requirement to the system. The same goes for things like branch entries pictured on the right. You can see that a 30-degree angle is preferred. All right, so our next component in the system design is the dust collector itself. So the main objective of a dust collector is to deliver sufficient efficiency while operating in a predictable, stable, and economic fashion. So in this photo here, essentially what you're looking at is a fiber laser and then stacks of different raw materials that are being staged to be cut. In many cases, if a company is getting its first fiber laser, or even its second or third, for instance, it's going to greatly increase their production efficiency and then capacity as well. And then just as a side note, in the back corner, you can see the blue box, as we call it, which is a blue Donaldson DFE cartridge collector. And that is the cartridge collector that is hooked up to this specific laser system. So although there are different types of collectors available on the market, cartridge collectors are what I would recommend for laser cutting applications. Cartridge collectors are typically smaller and have a lower initial cost than bag houses, and they are best for low to medium dust loads and fine uniform dry dust, like which would be generated in laser cutting applications. Cartridge collectors are also continuous duty, so they don't need to be turned off or shut down in order to clean the filters. And they use plant compressed air for the pulse jet cleaning system, which cleans the filters themselves. Here are a couple examples of recent laser cutting projects Donaldson has worked on. So as you can see, both are cartridge collectors and they're both located indoors. The one on the left is a cellular system that is connected to actually 3 different lasers. And the one on the right, which is an image you saw previously, is connected to a single machine located next to an enclosed laser. Also, as mentioned, even though most would be indoors, here's another example of a cellular system that is hooked up to multiple lasers. And the collector actually had to be located outdoors due to a space constraint inside the shop. So for single machine systems, sometimes the airflow will actually be small enough that we can use one of our packaged dust collectors, such as the DF Pre, which is shown here on the slide. This is a great option since everything you need is considered pre-packaged, meaning the fan and controls are essentially built into the collector, making it easy for installation, making it easy for a fast and quick installation.
Hey, Mike, can you explain by what you mean by small enough? Is there a particular CFM threshold you recommend for a package collector?
Yeah, so typically anything 3,000 CFM or less would be an ideal option for a package collector. The laser table would also normally be what we would consider a standard size table, so a 3015 or 4020, meaning 3 meters by 1.5 meters or 4 meters by 2 meters.
Thanks.
So here's another real life example of a package collector next to an enclosed laser table. So essentially what you're looking at here is like I said, another one of our package collectors. This one is called a Downflow LS. So this collector has a small compact footprint and has an integrated fan and control panel. The nice thing about the design, besides the fact that it is small and takes up a small space on the floor as far as footprint, is that it is relatively quiet, which is nice when most times, like we mentioned, it will be located indoors and then also will be located in close proximity to the operator or other people nearby. So in terms of the filter media inside the cartridge collector, I would typically recommend a nanofiber filter. What this does is it allows for a dust cake to form on the surface of the filter, ultimately creating a higher efficiency media. I also recommend a flame retardant style media for laser cutting, just because of the sparks that are present in the laser cutting process and could be transported to the dust collector. And then also, as mentioned a couple slides ago, in most cases, these dust collectors are located indoors, and depending on the material being cut, the exhaust returned to the facility and the dust could be considered toxic. Such dusts include, but are not limited to, aluminum and stainless steel. In these cases, we would recommend a HEPA afterfilter, which are 99.97% efficient in capturing. All right, so moving on to the last system component, or one of the last system components, the fan. Let me explain how we size and choose a fan. So the fan has two main job responsibilities. So first, it must deliver the necessary volumetric flow at the required static pressure to drive operation of the system. And since many of the dust collectors can operate with clean or dirty filters, the required airflow must be maintained over a range of static pressures, whether the filters are clean or they're dirty. And then secondly, the fan you select should be able to deliver the desired static and airflow with an appropriate energy efficiency at an acceptable sound level. For example, non-material handling fans located on the clean side of the collector are going to be more efficient than material handling fans located on the dirty side of the collector. So there are two basic types of fans used in laser cutting, the first being a backward inclined. It has solid flat blades and is capable of handling light dust and medium to high amounts of airflow, like those generated during the laser cutting operation. It's up to 80% efficient, and on the slide shown here, you are looking at an example of what a backward inclined fan might look like. The other common type of fan used for laser cutting systems is a radial blade style fan. So this fan is less efficient and louder and typically has a paddle style wheel. In general, for our larger dust collectors that are requiring more airflow, we would be using a backward inclined fan. But a radial blade fan, which you're looking at here, is most often selected because it is more cost effective and designed for smaller systems. All right, so once you have selected your fan type, a critical component of the fan design is static pressure, which John did mention earlier. Static pressure is basically defined as a resistance that the airflow must overcome due to system components. When we design a system, we calculate the total system static pressure so that we can size the fan properly. So what you're looking at here on the slide is actually an example of a system that we have designed numerous different times. So kind of walking through what we're looking at here. So the laser table itself accounts for 4 inches of static, the ductwork, 1 inch of static, the filters in the collector, we account for 4 inches of static. This is what we would consider a worst case scenario when the filters are dirty, because new filters will have a much lower static pressure of say 0.5 inches of static. And then as the filters themselves age or load with dust that is not pulsed off, will increase the static of the filters themselves. And then the spark cooler would account for another inch. So the total system static, when you add all of those up, would be right at 11 inches. And then the required airflow for this specific table was 2,000 CFM, which is provided generally by the laser manufacturer itself. All right, so fans are sized based upon the system's total static pressure and the required airflow. Let's say I need to size the fan for the recent project we had that we just reviewed, 11 inches of static at 2,000 CFM. When looking at the fan curve, what we would do is locate the static pressure of 11 inches and line that up with the required airflow of 2,000 CFM. And when we line those two factors up, we land on a TRB 10 on the fan curve. This means we would select a TRV 10, which is a 10 horsepower fan, where those lines intersect, as you can see on the slide. All right, so moving on to our next topic, spark mitigation. So since lasers, as mentioned, will generate sparks on the application itself, I wanted to briefly talk about this topic. One method that we can use to help reduce fire risk is an ignition source mitigation strategy. A variety of options do exist, such as dropout boxes, inline spark traps, specialized inline spark abatement devices, spark detection and quenching systems, dust collector location, and material-specific systems to prevent mixing of incompatible materials. Here's an example of a spark-reducing inlet that we use on our DF-free collector. So essentially what this does is, as the air comes up from the bottom in the inlet, it forces the air through a tortuous path, and that air will then travel through different directions, which essentially will help knock down the sparks. Another option would be an inline spark trap, which would be located within the air intake duct, as you can see from this picture. In the image, you actually see two DFE cartridge collectors sitting next to each other, and then the one on the right has a spark cooler, which is the black piece in the ductwork. And essentially what that does is it creates turbulence in the airstream that cools and arrests most sparks without the use of water or chemicals. So let me show you a quick video on the next slide, and you can see how it works. All right, so essentially what you're seeing here is metal grinding application with no spark cooler. And then when we introduce the spark cooler to the system, you can see the application generating sparks going through the spark cooler, and then out the other side of the duct there are no sparks that are passing. So that just shows you the effectiveness of the spark cooler itself. All right, so the last section we're going to cover today before we get into the Q&A portion is electrical controls. As the name implies, they monitor and regulate the entire dust collection process to ensure efficient and safe operation, maximizing performance and minimizing downtime. They can range from very simple to incredibly complex, like the controls you're seeing here from a system we installed recently. Electrical controls are capable of turning the system on and off, monitoring and controlling the airflow, running the cleaning system, displaying differential pressure, which is important to help understand the condition of the filters, alerting the end user when there's an issue, such as when it's time to change the filters or empty the dust bin, controlling ancillary equipment, such as explosion mitigation devices, and remote monitoring of the system. Because they can be quite complex, specifying the best electrical control for your customer can be complicated. So running through kind of the different types of controls, we'll start with the most basic type. So the most basic type of control is a motor starter. And what this does is it turns the fan motor on and off with manual buttons, and it protects the motor from short circuits and overloads. A motor starter is often paired with some kind of gauge to monitor differential pressure in the collector, which tells the operator the condition of the filters. For laser cutting applications, I generally recommend a basic or advanced custom control panel. So when looking at a basic custom control panel, what we're doing is we're typically combining motor starters with a digital differential pressure reading. It allows the operator to determine set points for cleaning, both high and low. High is when cleaning would be initiated in the system, and low is when cleaning would be stopped. And it cleans while the collector is in operation. There's also a downtime cleaning option, which means that the collector can be set to clean when the laser table is not in operation, such as the end of a shift. It's a more integrated solution than a motor starter and gauge. Getting into a more advanced custom control panel, in addition to everything we've discussed so far with the basic control panel, this panel allows for things such as remote interlocks and integration of ancillary equipment. Interlocks are very common and are set up so the dust collector will turn on or off with the laser table, since the dust collector only needs to be running when the table is cutting. An advanced custom control panel typically utilizes electronic airflow control instead of manual. And at Donaldson, we strongly recommend using this electronic airflow control or alongside with a VFD, which we'll discuss shortly. So when you're looking at the system itself, because the static pressure does change due to filters as they age or load with dust, it's important to consider how to control the airflow when you design a system. We can control the airflow using electronic or manual configurations. So for manual airflow control, the fan will need to have some type of mechanical damper or slide gate so the operator can manually adjust the airflow entering the duct. They generally have a lever so that the operator can open or close or move the lever or open and close the damper as needed. For example, immediately following a filter changeout, it should be closed to the point that maintains proper airflow. And then throughout the life of the filter, the operator should adjust the damper as needed to maintain the design airflow. This adds a lot of room for error, which is why most OEMs are recommending electronic airflow controls. So walking through an electronic airflow control with a VFD or variable frequency drive, essentially what this does is it automates the fan motor speed so that the fan is used only as much or as little as needed for optimal performance. For example, when the filters are getting towards the end of their useful life, the VFD would then speed up the fan to overcome the additional static pressure so the system is still performing at designed airflow. Because it removes many variables of the system performance, we strongly recommend specifying a VFD. It's definitely a worthwhile investment to minimize risk. And just as a heads up, it's important to work with your fan manufacturer to understand the airflow requirements. Often they will recommend oversizing the fan slightly to allow for the maximum benefits of a VFD if you were to use that in your system. If the system has ancillary components, you can specify that they are integrated with the control panel. Explosion mitigation devices like fire suppression, isolation valves, and explosion vents are incredibly common and need to be programmed on the control panel to ensure that the system will shut down appropriately if there were to be an event. Just know that when ancillary components are integrated into the panel, startup and shutdown sequencing of them is important. So we also wanted to mention that many dust collector manufacturers are now offering the ability for operators to monitor their systems remotely. At Donaldson, we call our remote monitoring system IQ, which essentially makes the dust collector smart. This allows the customers to be able to maintain their collectors remotely, which could be for a single collector, a single location, or larger companies that have multiple collectors in multiple locations. It provides customers with real-time data, alerts them when there's an issue, and provides historical reports. As you can imagine, customers find this incredibly beneficial. Again, most manufacturers are heading in this direction and customers love it. It's definitely something to consider when specifying a system.
All right, well, thank you. Great job to both Mike and John. Designing dust collection systems can be complicated. There's a lot that goes into it. We get that, but that's what we're here for. We've sold countless systems around the world. We have local support in your market, and please know that we are here to help in any way that we can. So we're going to finish up with some Q&A. Trainers, you can turn your cameras back on. I'm going to turn mine back on as well. So just a heads up that everyone who attended will receive an email that includes your professional development hour credit. There's a few questions about that in the chat box, so just know that that's coming. There's a few QR codes you can scan if you're interested on the screen there, just to let you know. The on-demand webinar page does include a form that you can fill out if you're interested in doing more of an in-person lunch and learn or something more customized for your team. We can help you with that as well. And if you have follow-up questions, or if you didn't get your PDH certificate maybe a week, every once in a while it gets stuck in people's spam folders. John's email address is on the screen and he would be happy to help you with that. All right, so let's go to our first question. Let me move my chat box here just a second, you guys. All right, so we're going to kind of go back to the beginning here. Oh, we got that one already. All right, so question about what area you should be using for velocity. There's a couple of different questions about this. I don't know if you guys can see the chat box. The follow-up question, a different question on the same topic. I use 300 feet per minute downward. Do we need less than that for his laser at like 150 to 200? There is a couple different questions about that. Wondering if one of you guys could respond to that.
Yep. So when we're talking about for plasma versus laser, so typically, I guess there's a couple different ways you can look at it. So the actual duct velocity capture at the hood itself, where we would be pulling the air out of the table, typically we would be looking around 150 feet per minute. A lot of times, though, the downdraft velocity of the table itself, pulling from where the application or the laser beam is, would typically be around that 200 to 300 feet per minute. So that's something to notate. So for the person who mentioned 300 feet per minute downdraft at the table itself, that would be accurate.
Gotcha. Okay, so thank you for clarifying that. All right, so our next question, and that's a great question. Do filters have some sort of an alarm telling you when they're full?
Yeah, so we mentioned the different types of controls, and John, you can add to this too if you'd like, but on some of our more, I think we call them simple custom controls for laser, they're going to have a delta P or a pressure reading on the control panel itself. So typically, there won't necessarily be an alarm, but it's something you can monitor. Some companies actually do set up shutdown points for their overall system application based on filter loading, but the dust collector itself isn't going to automatically turn off if the filters are full, but you can monitor the differential pressure on the reading.
Yeah, whether it's a gauge or a delta P that's measuring the sag pressure. And usually we recommend getting about anything over 4, once you get to 4, is when you either want to clean, or if you continue to clean and you can't get below a 4 on the sag pressure, then it's time to change the filters. So there's a couple different ways to gauge that. Most of our systems will have an ability to look at the sag pressure, and when you get over that level of 4 is when you have to start looking at cleaning or changing out those filters.
Thank you. All right, next question is related to AMR. What AMR is recommended for laser cutting applications?
Yeah, so typically when we're looking at fiber laser, I mean, it can really range. Everyone does it a little bit different, but we typically try to look at about a 1.5 to 1. Could be 1 to 1. It just kind of depends on the table itself, and the power of the laser is also an important factor in looking at AMR. So typically, let's say you have a 3 kilowatt table, that's going to be cutting slower, producing less dust. So you could have a higher AMR, but if you get up to a table, let's say for instance, 30 kilowatts, or I know someone mentioned in the chat, there's even tables that go up to 100 plus kilowatt powers. You would want to adjust your AMR appropriately, so you would want to be less aggressive in that case, because the amount of dust and the speed at which it's generated is going to be significantly higher. And then if you're looking at plasma, which is going to typically be a little bit heavier loading, with particulates a little bit different, the air to media ratio is going to be, let's say, 2 to 2.5 to 1. All
right, thank you. Next question. Do you know where is the explosivity risk coming from if the metal is burned and oxidized?
Yeah, so I know we mentioned this is kind of a complex
Yeah.
topic when we're talking about this. So essentially, the first thing you'd want to do, so let's say you're going to have a new laser installed at your facility. So the thing that NFPA guidance would recommend is that you get your dust tested. So essentially, that's the dust hazard analysis we mentioned previously. That's going to determine if the dust truly is fully oxidized, because to that person's point, that's kind of the key factor here. We can't always guarantee that the dust is going to be fully oxidized. And if the dust is not, that's a contributing factor to an event that could possibly occur.
Okay, so
And then also,
sure their dust is tested, right? So you know exactly what you're dealing with.
yeah, yep, that's the best way to go about doing that. Yep.
And then what were you going to say, Mike? Sorry, I didn't mean to interrupt you.
Oh no, you're fine. And then obviously mixing metals, which was mentioned in this presentation as well. That's something that also can cause explosivity depending on what the metals are. So once again, something to consult with your local AHJ.
Okay, so next question, is condensation a concern with a filter unit located outside? And if so, how is that concern addressed?
Yeah, so our dust collectors, depending on the collector itself, are designed to be outdoors. If they are not, there's small modifications we can make to them so they can be outdoors. But yes, condensation would be a concern because cartridge collectors perform their best when the dust is dry and they're in a dry environment. So typically, we would want to make sure that the dust collector has, let's say the collector, like a package collector, which we discussed earlier. We'd want to make sure that that has a rain hood over the exhaust to eliminate moisture from getting into the collector. And then we'd also want to make sure that obviously you have sufficient ductwork. So we mentioned spiral duct, which could allow rain to entrain inside the duct and then be pulled into the collector. You would just want to make sure you avoid that.
All right, thank you. Next question, can dust accumulate inside of a spark cooler?
So I would say I'm not 100% sure if it can, but what I would go back to is if you have sufficient duct velocity, which we recommended earlier, that should avoid dust buildup anywhere inside the system of ductwork. So you'd want to maintain that 200 to 300 feet per minute.
Yeah, it's a pretty open, pathway that kind of diverts air. Doesn't really, it's not intended to build a dust cake. So I haven't heard that where a spark cooler needs to be, cleaned out, or even our own, spark reducing options need to be cleaned because it's more diverting air than collecting dust.
All right, thank you. Next question, what do you recommend for laser cutting applications that generate some smoke that can load filters greatly due to their lifespan and reduce their lifespan, sorry?
Yeah, so I guess I would need maybe a little more context to that question. I mean, typically what you are capturing is smoke, fume, and then the fine particulate. So typically, the filters we'd recommend, the velocities we'd recommend should capture all that smoke and particulate and fume. Mm-hmm. There is one thing that I could mention on this topic. So some materials, whether they be pickled or oil material or like a galvanneal or galvanized steel, they do have coating on them. So when they're cut, they do generate what we would consider a sticky dust. So in those instances, you would have a couple options. One, you could use a continuous lime injection system, which essentially would coat the filters so the dust does not stick directly to the filter media. And then I've also heard in those specific instances, if you cut with pure nitrogen or cut with nitrogen, versus shop compressed air, it's also going to reduce the sticky contaminant on the filters.
So if they're seeing some excessive loading on the filters, something's going on that needs to be addressed, right? Something's not quite right in the design, or we need to pre-code the filters or do something different in the design.
Yeah, that would be a kind of a case-by-case basis, and you could reach out to, anyone at Donaldson, and we should be able to help assist.
Okay. Perfect. Thank you. All right. So our next question is, what's the difference in calculation for open versus enclosed machines? And do you use sheet coverage to reduce the open area? It's kind of the managing open versus enclosed. Or how the design's different.
So whether the table is open or enclosed, typically the manufacturer is going to have a specification for airflow. And for open tables, we typically see about 50% required coverage on the table, meaning if you have a really small piece of, let's say, metal that you're cutting, the whole table is still pulling ambient air. So it's going to be very difficult to capture the air efficiently if only a little bit of it's covered. So typically the requirement would be to cover 50% of the table outside of the piece that you're cutting if it does not meet that requirement.
Okay. All right. That makes sense. Another follow-up question about capture velocity. Is the capture velocity of 150 feet per minute measured across the face of the hood? I feel like we kind of addressed this, but let's just make sure that their question was answered.
Yeah, the point where the fume, dust, and particulate is being exhausted to the ductwork of the collector should be at a minimum 150 feet per minute. Hopefully that answers the question.
So the next question, I'm not really sure exactly which system they're talking about, but what types of challenges have the implementation of this system had? So maybe a couple of common challenges you run into, Mike, when it comes to laser cutting systems.
Yeah, I would say, the biggest thing is just doing your homework ahead of time. So making sure you have enough airflow through your ductwork, making sure you have enough filter media to handle the dust and fume and particulate that the laser will be generating. Typically, I think the biggest challenge we're seeing nowadays is as the laser powers continue to grow and they cut faster, they cut more material, you run into folks trying to use the same dust collector maybe they used 5 years ago. That may not be an applicable solution for today's lasers. So something you're definitely going to want to look at. So I would say undersizing the dust collector itself would probably be the biggest challenge that we run into.
Well, and the result of that would be fire, right? Every OEM wants to avoid fires, and occasionally, we will hear of an issue out in the field where, a system wasn't set up right and results in a fire, and everybody wants to avoid that and the repercussions of a fire. The other thing we've heard recently, Mike, as well, is with these higher powered laser systems, if you don't have a well enough design, dust collection system, it will interfere with the quality of the cutting and the laser itself, as that particulate can interfere with the beams.
Yep, correct.
Thank you. All right, we just had a question just submitted. Does the AMR change depending on the sheet thickness? Does that make any sort of difference in the design?
So typically when we're providing a dust collector, we're most likely not going to know the specific details always of what the customer is necessarily cutting or the thickness of it. I think the thickness of material that is being cut would be driven by the laser capabilities themselves. If you're, the more homework or investigation you do up front is definitely beneficial. So, if you know that a customer has, for example, a 20 kilowatt laser that they want, and they're always going to be cutting, let's say, 1/2 inch thick material, and they're running 24/7 versus 8-hour shifts, you're definitely going to want to size the AMR more conservatively. So think of the thicker the material, the more they're cutting, the more media you're going to want to have present on the system.
Thank you. And that looks like that was our last question. So thanks to all of you for joining us today. Thanks to Mike and John. You guys did a great job providing us with great information. And again, we'll make sure that all of you get your PDH credits in your email. And if you don't see it in about a week, make sure and reach out to John and let us know. Thank you, everyone. Have a great rest of your day.
Thank you.
Thank you.